This talk is sponsored by Livepeer. Livepeer is a decentralized video streaming network that provides the necessary infrastructure for broadcasting video over the internet at a fraction of the cost to today's cloud infrastructure. Learn more at livepeer.org.
Okay, so hello everyone, my name is Rasmus, and today I want to talk about how we launched the Pixel Devs NFT collection on Polygon. So first, a little bit about me. I'm a full stack developer and consultant based in Denmark. I have worked with web development for more than 15 years, and my journey into Web3 first got started last year when I became a Developer DAO member. And without further ado, let's just jump straight into it. So, Pixel Devs. What is Pixel Devs? It is a NFT collection of NFT. It is an NFT collection launched recently just by Developer DAO, and it is a derived NFT from the original Genesis NFT, also known as Developers for Revolution. It's a visualization of the 8 traits, and what you see here on the left is my personal Genesis NFT, and on the right you have the Pixel Dev NFT. So I first got involved with the project when I built a simple preview app that allows you to put in your Developer DAO token ID and see a preview of your Pixel Dev. Later on, that very same web app laid the foundation for the minting site that is today public at pixeldevs.developerdao.com. So what I want to talk about today though is how is the actual underlying workings of the code, which is we decided quite early on to launch the NFT collection on a layer 2 option, and we chose Polygon. Now, our motivation for that was quite straightforward: to save a ton of gas money for our members, making it more affordable and accessible to claim your personal Pixel Dev. Now, it also came with a further complication, which is in order to mint your Pixel Dev, you must also hold a Genesis NFT on Ethereum. But how do we make that a check cross-chain? So if you're anything like me, a savvy Web2 developer, you might think, hey, that's not too difficult. What we'll do is just the web client will send a minting request to Polygon, and Polygon will then check in with Ethereum and see, hey, does this address hold this token in the Genesis token? There's just one problem, which is it's not how smart contracts and blockchains work. So a smart contract runs in a deterministic environment, meaning that a certain input must always provide a certain output. And with that, it comes to restrictions of not being able to make any kind of randomness and not make any kind of outbound network requests. It can only interact with itself and the blockchain that it's hosted on. So what can we do instead? Actually, we have a few different. We have quite a few different ways to do this. But what I'll share with you today is specifically how we ended up doing it. So basically, we took that responsibility and put it into what I like to call a authorization server. So the flow now looks like this: the browser, a user logins with the wallet in the browser, in the web client, and from the web client it will then make an authorization request to the authorization server. That request contains the address of the user that's authenticated and the token ID they're trying to mint. Now the server will then check in with Ethereum and ask, hey, who is the current owner of this token ID? And if that address that comes back matches the address in the request, it will create a response containing the address, token ID, and a expiration, which is how long, and then it will create a signature with those 3 parameters. And the expiration is simply how long is the signature valid for. Next, the web client will then send the actual minting request containing this payload from this response from the server. And all Polygon has to do now is see, does this signature look like a legit authorization server signature? And if it does, then I can go ahead and mint the NFT. But there's one last piece to the puzzle, which is how does the Polygon contract know what a server signature looks like? For this to work, the authorization server will need to have an identity on its own, which is basically a wallet address with an underlying private key. It can then use the private key to create the signature, and the Polygon contract can then see if the entity that's created the signature came from the known server address. And if it did, we know that the user holds a Genesis token on Ethereum. So there's a few benefits to this approach. One of them being that it's super flexible in the sense that it works with any kind of EVM compatible blockchain, being any layer 2 option, or can even check against, it can even run on, say, Polkadot parachain, as long as it's a EVM compatible blockchain. It can also incorporate any kind of logic you may wish. Basically, if you can write it in code, you can build it. It's super flexible because you can push updates to the server, bug fixes, new features, and it's also very low cost. All you have to pay for is hosting of that stateless server. There's also a few things to keep in mind, which is it does have a private key that needs to be kept safe. If that private key is somehow exposed or exploited, then it can be used to forge the server signatures, and your solution is no longer secure. And yeah, there's also the extra dependency that you add to the contract, which is the server. So that's of course something you want to keep in mind. If you're interested in knowing more about our considerations and also some of the other solutions we did explore before heading down this path, I highly recommend you to go check out a blog post I published recently. It's on the official Developer DAO blog, and it's called Launching Pixel Devs NFT on Polygon. So go check that out. What I want to spend the rest of my talk on is showing you the actual code that powers our solution. So let me just share my editor here, and we'll actually do a code dive. So what I have here is the Git repo of the Pixel Devs project. It is called Pixel Avatar, so that was our code name for the project while developing it. So just keep that in mind. Whenever you see Pixel Avatars, it actually means Pixel Devs. You'll see that our project consists of three main parts, which is the contract, the web client, and the server. So we will zoom in on the actual communication between the server and the contract. And let's try and start by opening up app.js and of the server, and you'll see that it's a very basic Express server. If we scroll down here, there's two endpoints. There's inventory, which returns an array of token IDs that the provided address holds on Ethereum. And then we have the authorize method. And let's try and open that. So at the top of the method, we are fetching the address and the token ID from the request. We'll do some very light validation that a token ID was actually provided. And next we will send a request to Ethereum asking who is the current owner of this token ID. With a little bit of luck, that address should match the address provided in the request. And if it didn't, we're going to error out saying that only the owner of the Genesis token can claim this token. We're then ready to create our signature. We'll start by creating a deadline, And the deadline is basically just a sanity check saying that you can't just obtain a signature and have it lying around for forever. You need to use it fairly soon. And basically we want to keep it that window as short as possible, but long enough that a user can actually make a successful transaction on Polygon. I think right now we have it set to 5, 10, 15 minutes, something like that. We'll then construct a message, and the message is a concatenation of the different parameters. So it basically reads token ID colon the actual token ID, address colon the address, deadline colon the deadline. Next, what we'll do is that we will hash it, and for the hashing we use a algorithm, I believe it's called KEKAK 256, and that is the hashing algorithm that Solidity also uses in the contract. Finally, we will create our signature. Now, I won't go too much into how we're constructing the signature, but basically we give it a hash and a private key. We will then sign it, and finally the outcome will be 3-part, which is consisting of V, R, and S, and that together forms the signature. Now, if you want to know more about how this works, I recommend you to go Google it and find it on Stack Overflow. There will be someone explaining it much better than I can. Also, what I'll mention is that the private key of the server is, so we have a CLI script that generates random key pairs. So we can just run the script and it will spit out a private key and a wallet address derived from that private key. The inner workings is exactly the same as when you download MetaMask, and it will provide you with a wallet address with an underlying private key. So it's exactly the same basically. In our response, we'll then include the token ID, the deadline, and the signature. Now, you'll notice that we are not actually returning the address, and that's because when the user then creates the minting request, it will already, the payload of that request will already include the authenticated wallet address. So that's what we'll use instead. Let's go and check out on the contract part of things. So the contract here is, you'll see that it's a ERC 721 enumerable upgradable contract from OpenZeppelin. And if you don't know what that means, it basically just means we didn't go and write our contract from scratch. Instead, we built upon the tried and tested OpenZeppelin contract, so we only have to implement a few details that makes our contract unique. And you'll see that we have a base URI, which is the IPFS address, where the actual images are hosted along with the metadata. We have the minting price, and then we have the server address. And mind you, again, this server address is the public address of that server, derived from its private key. So those two should align with each other. I'll skip through these fairly quickly. We have some events that are being emitted, and we then initialize the contract, and then we have some getters and setters here. Now I'll scroll down to the actual method that we call from the web client, and it's called mint with signature. Again, you'll see it accepts the exact same parameters returned from the server. We have the token ID, deadline, and the signature. The body of the minting method is very simple. We just check that enough matic was sent. We will then mint the actual NFT and emit an event saying that it was minted. Now, what you'll notice is that we have this modifier here called valid server signature, where we pass in the arguments. And this tells Solidity that before you can jump down and call this code, you must make sure that this code up here passes first. So let's have a look at what that is. So this is the modified valid server signature, and the first thing you'll notice is that we are reconstructing the message exactly the same way that we did on the server side of things. So we are concatenating these parameters, token ID, address. You'll notice that the address is the message sender, which is the actual wallet address that initiated this transaction. And finally, the deadline. We then use the same hashing algorithm, and we pass it into a function called easy recover. Now, what easy recover is, it takes the hashed method and the signature, and what it will spit out is the wallet is the address that created the signature. And with a little bit of luck and no foul play, that signer should match the server address known to the contract. If it didn't, we're gonna error out with invalid server signature. Now, if it didn't match, the last thing we'll check is that the deadline hasn't expired. And finally, we are telling Solidity, if you can make it to this point, you're good to go. You can go ahead and mint the NFT. Now, there's just one more thing I'd like to address, which is there's something that tripped me up a bit while building this, and it has to do with the way Solidity works fairly close to the metal, if you will, in the sense that the way that we concatenate these different parameters is that some of these are strings, and some of them, for instance, the address is actually a hex code. So you can't just concatenate those like one big string. Instead, what you use is a function called ABI encode packed. And what that does is that it loops through each of these different parts. It will then hex code them until they're all hex codes, and then it's gonna concatenate those hex codes. Now, just hopping back to the server, if you're anything like me, what you would do is just a bit optimistically concatenate the strings, so it reads the actual like token, address until it's one long string, and then for the sake of it, you can hex code that. The problem is that these two different approaches does not produce the same output. Basically, concatenating hex codes is not the same as concatenating a string and then hex coding that. So instead, what I ended up doing here was create a little helper called hex concat that loops through each of the different parts, each of the different strings, ensures that it's a hex code, like hexen codes it, and then by the end of that, concatenate the individual hex codes. And that will produce the same result as what we get in Solidity. So I hope that I just saved you a few hours of debugging, because it sure did trip me up, and hopefully you won't have to spend those hours now. Okay, so finally, I just want to say special thanks to the other core members of the derivatives team, Goldsulu, Brian, and Eric, obviously, who is the great artist behind all of these pixel devs, and also to the countless other contributors to the project. It indeed was a team effort, and it's been a blast working on it together. If you're a Developer DAO member, do go check out the pixel devs on the website. And yeah, my name is Rasmus, and I hope you found this talk interesting. Do feel free to reach out to me on Twitter or GitHub or Discord if you're a DAO member. And yeah. Oh, by the way, if you've been wondering what this behind me is, it's actually my wife's NFT collection. It's on OpenSea. It's called Buttergoods. So it also just goes to show that we are pretty red-pilled on anything crypto, Web3, NFTs here in the house. So yeah. Thank you so much for tuning in, and have a great day. I'll be seeing you. Bye.